Buenos dias. Today we're going to look at differentiating the inverse trigonometric functions. We're going to start with inverse sine. So let's consider the function y equals inverse sine of x. Now, we don't know how to differentiate inverse trigonometric functions yet, but remember that this is equivalent to saying that sine of y is equal to x, right? The inverse sine function is defined to be the inverse of sine. So if we look at sine, we can switch the input and output variables, and we get sine of y equals x. And now that we have it written like this, we can implicitly differentiate both sides with respect to x. So we can differentiate the left-hand side with respect to x, and the right-hand side. And then we'll be able to, hopefully, figure out what the derivative is, what y prime is. So on the left-hand side, when we differentiate sine of y, the derivative of sine is cosine. So we've got cosine of y times y prime. Remember, we've got to use the chain rule here. Y is a function of x. So we've got that y prime. And then on the right, the derivative of x is just 1. Now, to get y prime alone, we divide by cosine. So this is going to be y prime equals 1 over cosine of y. Things are looking good so far, but we really want to have this in terms of x, if at all possible, right? We don't want the derivative in terms of y if we can actually write it in terms of x. Now, we've got a y here, but remember, y is equal to inverse sine of x. So we can replace y with inverse sine of x, and that gives us 1 over cosine of inverse sine of x. So we actually have a composition of a trig function and an inverse trig function. And we can use a right triangle to see how this simplifies, because we can actually write this without dealing with inverse sine of x inside of cosine x. So remember, inverse sine of x is asking which angle gives us a sine that's equal to x. And so if we're looking at this angle theta, and we say that it has sine equal to x, well, sine is opposite over hypotenuse, so we could write x and 1 here. So because this angle theta has a sine equal to x over 1, which is x, this angle theta is actually inverse sine of x. So we can write this now as 1 over cosine of theta, because theta is the angle that gives us a sine of x. Now all we have to do is evaluate cosine of theta. Cosine of theta is adjacent over hypotenuse. So we need to know the value of this adjacent side, the length of that adjacent side. We know the Pythagorean theorem is going to give us that here. This is a right triangle. I forgot to mark it. The Pythagorean theorem says that the adjacent side squared plus x squared equals 1. If we subtract x squared from both sides, that tells us a squared is 1 minus x squared. And if we take the square root of both sides, that gives us a is the square root of 1 minus x squared. So we can write that here. And remember, the denominator is just cosine of this angle theta. Well, cosine is adjacent over hypotenuse, so that's going to be this square root all over 1. And anything divided by 1 is itself, so that cosine is equal to just the square root of 1 minus x squared. And so this is our derivative of the inverse sine function. We've got 1 over the square root of 1 minus x squared. It's actually really fascinating. When we had regular trigonometric functions and we took the derivatives, we got trigonometric functions. When we have polynomials and we take the derivative, we end up with polynomials. When we have exponential functions and we take the derivative, we end up with exponential functions. But when we have inverse trigonometric functions and we take the derivatives, we're going to end up with these interesting algebraic functions with x's and squares and square roots and whatnot. And that is different from what we've seen before. And the reason for that is because the Pythagorean theorem allows us to take trigonometric ideas and express them with an algebraic relationship. So at this point, we have the derivative of the inverse sine function. We know the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. And once we have this formula, we can use it to differentiate different functions that have inverse sine of x in them. Let's do one quick example together. Let's differentiate y equals inverse sine of x squared. Okay? We're going to have to use the chain rule here because we have a composition of functions. We start with the derivative of the outer function. The derivative of inverse sine of u is going to be 1 over the square root of 1 minus u squared. But u is x squared here, so that's going to be x squared squared under that square root. And then because we're using the chain rule, we have to multiply by the derivative of the inside. The derivative of x squared is 2x. And so we can combine those into one fraction and simplify the denominator. This gives us 2x over the square root of 1 minus x to the fourth. And that is our derivative. In the next video, I want us to derive the formula for the derivative of inverse tangent. And once we do that, we're going to do another quick example problem, and I will give you a table that shows you the derivatives of all 6 inverse trig functions.